In a glass case in a corridor in Oxford, a small brass bell has been ringing twice a second since about 1840. Nobody is allowed to open the case, because nobody wants to be the person who stopped it. 186 years, something like 10 billion rings, and as far as anyone can determine, that is the longest any powered object human beings have ever built has kept working. Now hold that against the journey. 1 light year, at the speed of the fastest thing we have ever launched, takes 17,600 years. The best fuel we fly into deep space loses half its power every 88. Nothing we have made has survived 50 years out there, so every claim about 1,000 is a guess wearing a number. And the hardest item on the list is not on the spacecraft at all. By the end of tonight, you will know exactly what it takes to cross 1 light year, and exactly what is waiting at the other end. Get comfortable. If you enjoy finding out that the obvious obstacle was never the real one, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word away is going to stop meaning what you think it means. Now, let's gently drift into this. Somewhere in the room you are in right now, there is a small light. It might be a lamp on a bedside table, or the standby glow on a television, or the thin bar of light under a door from a hallway someone forgot about. Look at it, or just think about it, and consider what that light is actually doing. It is not sitting there. It is leaving. Every fraction of a second, that little source is throwing out light in every direction at once, and almost all of it never reaches your eyes at all. It crosses the room, it strikes a wall, and it stops. But a small amount of it does not strike anything. A small amount of it goes out through the window, or would, if the window were open and the curtains were pulled back, and that portion of the light from your room does not stop. It keeps going. And what I want to do tonight, before we talk about ships and fuel and engineering, is follow it. Give it 1 3/10 seconds, and it has passed the moon. That is roughly the time it takes you to say the word moon out loud and then take a breath. Give it 8 minutes and 20 seconds, and it has crossed the entire distance from here to the sun. That is about the length of a song. Give it 4 hours and it has passed Neptune, the outermost planet, at the far edge of everything most of us were taught to think of as the solar system. 4 hours. You could fall asleep and wake up again in less time than that. Give it about 22 hours, and it catches up with Voyager 1, the most distant object human beings have ever made, which has been flying without stopping since before most people listening to this were born. Just under a day. The furthest thing we have ever built, and the light leaving your room tonight passes it before this time tomorrow. And then it keeps going. There is nothing there to stop it. It goes out through the last of the sun's influence, out through territory that has no name, because nothing has ever been there to name it, and it keeps going for 1 entire year. Not 1 year of watching it. 1 year of your life happening while it travels. You go to sleep tonight, and it is still going. You wake up. You have breakfast, you go to work, you come home, you sleep again, and the light is still going. A season changes. Then another. You have a birthday. Somebody you know has a baby, or moves house, or gets a new job. Winter comes back around, and you are wearing the same coat you were wearing the night this started, and the light from your lamp is still traveling, and it has not arrived anywhere, and it will not arrive anywhere, because there is nothing where it is going. That is 1 light year. It is not a measurement of size. It is a measurement of patience. And it is the smallest distance in this entire subject. That is the part that catches people off guard. When astronomers talk about the universe, they use light years by the 1,000 and the million and the billion, and it is easy to hear the phrase so often that it stops meaning anything. But one, on its own, a single one, is already the smallest interstellar unit anybody uses. There is no shorter journey out there. If human beings ever go anywhere beyond this star system, 1 light-year is not the trip. It is the first installment of the trip. So the question tonight is what it would actually take to cover that first installment. Not in the vague way that question usually gets answered, with a picture of a sleek ship and a hopeful sentence about future technology. I mean the way an engineer would answer it, sitting at a desk with a blank sheet of paper, listing what would have to physically exist before anything left the ground. And I want to warn you now that the list is not the one you are expecting. Almost everybody, when they think about this, thinks about speed. They think the problem is the engine. That is what the films are about, and that is what most of the conversation is about, and it is completely understandable, because the distance is enormous, and the obvious solution to an enormous distance is to go fast. Here is the strange thing. The engine is the part we already understand. Not perfectly, not cheaply, but genuinely. We have written credible designs for machines that could reach a meaningful fraction of the speed of light, using physics that is well established and materials that mostly exist. Those designs sit in libraries. Some of them were drawn up before anybody listening was born. If the engine were the only obstacle, we would have argued about the budget for 50 years and then built one. The things that stop us are much quieter than that, and much stranger, and they all have the same shape. Every single one of them is a problem with time rather than a problem with distance. Think about what a journey of this length actually means as a stretch of calendar. If a ship could hold 1% of the speed of light, which is about 3,000 kilometers every second, which is faster than anything humans have ever built by a factor of well over 10, the crossing takes 100 years. A century. Longer than a human life, in a machine with no repair shop, no spare parts, no replacements, and nobody to call. And 1% of light speed is optimistic. The real spacecraft we have flown are far slower than that, and we will look at exactly how much slower in a moment, because the numbers are genuinely surprising. The honest range for the sort of ship we could actually describe on paper today runs from about a century at the wildly ambitious end to something in the range of thousands of years at the realistic end. Which means this is not a transport problem at all. It is a survival problem. Not survival in the dramatic sense, with alarms and countdowns, but survival in the boring sense, the sense in which a bridge survives, or a building survives, or a promise survives. Something has to keep working, unattended, for longer than any object humans have ever made has kept working unattended. There are 4 things on that list. 4 bills, and each one has to be paid in full before anything else matters, and each one is genuinely unsolved in a way that almost never gets talked about. A power source that still produces electricity after centuries. A body of metal and plastic and silicon that is still holding together after the same centuries, with nobody to fix it. A way of getting rid of heat in a place that has nothing to pour heat into. And, last and hardest, an organization back here that is still paying attention when the answer finally comes home. We are going to price all 4 of them tonight, in real numbers, with real hardware. And then, when the bill is settled, we are going to do the other thing the title promised, and go and look at what is actually there. Because that turns out to be the part nobody talks about at all, and it is genuinely stranger than the engineering. There is a place 1 light-year from here, in whatever direction you like. It has contents. Somebody has counted them, roughly, and the count is not what you would guess, and it changes the meaning of everything else we are about to work out. By the end of tonight, you will know exactly what it takes. and you will know what is waiting. But we cannot start with the bill. We have to start with the only real evidence we have, the one machine that has been out there long enough to teach us anything at all about what happens to hardware over decades of silence. It is still flying tonight. It is still talking to us tonight. And it is dying, slowly and predictably, of something nobody can repair and nobody can argue with. There is a piece of metal about the size of a small car, with a dish antenna on the front of it, roughly as wide as a dining table, flying through the dark at this moment with nobody aboard. It left Cape Canaveral on the 5th of September 1977. It has not been touched by a human hand since the day before that. And it is still working. Voyager 1 is the furthest object our species has ever made, and it is also the longest operating one, and I want you to notice that those two records belong to the same machine. That is not a coincidence, and it is not luck. It is the single most important clue in this entire subject, and almost nobody says it out loud. The distance record and the endurance record are the same record, because in this business, distance is bought with time, and time is the thing that kills you. Here is how fast it is going. About 17 kilometers every second. That number is genuinely difficult to feel, so try it this way. In the time it takes you to say the word Voyager, it has covered a distance roughly equal to a comfortable afternoon's drive. In 1 hour, it covers about 61,000 kilometers, which is more than 1.5 times around the Earth. It is, by any human standard, going extraordinarily fast, and it has been going that fast without slowing for 49 years. And at that speed, 1 light year takes it about 17,600 years. Sit with that for a second, because it is the number the rest of tonight has to work around. 17,600 years. If Voyager 1 had been launched by the people who painted the caves at Lascaux, it would still not have arrived. If it had left at the end of the last ice age, it would be somewhere around the halfway mark. Everything you have ever heard of in human history, every empire, every language, every religion, every city, fits comfortably inside the time it would take the fastest thing we have ever launched to cover the smallest interstellar distance there is. There is a moment coming up that makes this beautifully concrete. On the 18th of November 2026, Voyager 1 will be exactly 1 light day from the Sun. 1 day of light travel. It will be the first object ever to reach that mark, and it will have taken 49 years and 2 months of continuous flight to do it. 1 day of light in half a century of flying. And a light year, the thing we are actually talking about tonight, is 365 of those. So that is the speed problem, and it is real, and we will come back to it. But the speed is not what is going to kill Voyager. Something much slower is doing that, and it started the moment the spacecraft was switched on. Voyager does not run on batteries, and it does not run on sunlight. Out where it is, sunlight is essentially useless. The sun is just the brightest star in a sky full of stars, and a solar panel out there would produce a trickle. Instead, it runs on heat from a lump of radioactive metal. Inside a canister on a boom sticking out from the spacecraft's body, there is plutonium, and it is warm, and it will be warm for a very long time, and a set of devices called thermocouples turn a small fraction of that warmth directly into electricity with no moving parts at all. It is a beautifully simple arrangement. There is nothing to break. There is only one thing wrong with it, and it is not a fault. It is a property. The plutonium is slowly turning into something else. That is what radioactive means. And as it does, it produces less heat, and the spacecraft produces less electricity, and there is nothing whatsoever anyone can do about it. Voyager 1 loses about 4 watts of electrical power every single year. 4 watts. That is less than the power draw of the little standby light on your television. It is a rounding error in the electricity bill of a household. And it is, at this point, the thing deciding what humanity still gets to learn about interstellar space. The spacecraft launched with 10 scientific instruments. 10 separate ways of measuring the place it was flying through. Over the decades, as the 4 watts a year quietly accumulated into something that could not be ignored, engineers at Mission Control have been forced to make a series of decisions that are, when you think about what they actually are, quite remarkable. They have had to choose, one at a time, which of those instruments to switch off forever. Not repair. Not pause. Switch off, permanently, from a distance of over 25 billion kilometers, with a command that takes most of a day to arrive. On the 25th of February, 2025, the cosmic ray subsystem was shut down. That instrument had been measuring high-energy particles from outside the solar system since the 70s. On the 17th of April, 2026, the low-energy charged particle instrument was shut down. That decision bought the mission roughly 1 more year of margin. As of this year, 2 of the original 10 are still running. The magnetometer, which measures magnetic fields, and the plasma wave subsystem, which listens to the density of the gas the spacecraft is moving through. 2 out of 10. And the engineers working the mission expect that at some point in the late 2020s or the early 2030s, there will not be enough power left to run science instruments at all, and Voyager 1 will become a transmitter that says nothing except that it is still there, and then eventually not even that. There is a detail in that arrangement that makes it worse than the plutonium alone would suggest, and it is worth knowing because it applies to every machine of this kind we could ever build. The fuel is not the only thing decaying. The thermocouples are decaying too. They are made of semiconducting materials sandwiched together, held at a large temperature difference for decades on end, and under those conditions, the materials very slowly sublimate away from their hot surfaces, and the junctions between them gradually deteriorate. So the generator's ability to convert heat into electricity falls at the same time as the amount of heat falls. The real decline outruns the pure physics prediction, by an amount that varies from unit to unit and that nobody models precisely, because we have never had enough units running for long enough to build a proper picture. And the whole thing is running on a scale of power that would embarrass a kitchen appliance. Voyager's radio transmitter, the thing shouting across 25 billion kilometers of nothing, runs at about 23 watts. That is a dim household bulb. The signal that reaches Earth from it is so faint by the time it arrives that the receiving dishes are picking up a quantity of energy which, gathered continuously since the launch in 1977, would still not be enough to noticeably warm a cup of tea. The onboard computers, all of them together, hold about 69.5 kilobytes of memory. A single photograph taken on your phone is hundreds of times larger than everything Voyager can remember at once. Its twin, Voyager 2, launched a fortnight earlier and traveling a little more slowly on a different path, is in exactly the same situation, losing power at the same rate, having instruments retired on the same kind of schedule. 2 machines, 1 dataset, both running down. Here is why I have spent this long on one spacecraft. Voyager is not a cautionary tale about old technology. Voyager is the single longest experiment ever conducted on the question we are asking tonight, and it is the only one there is. It is the entire data set. Everything humanity knows about what happens to a machine left alone in interstellar space for decades comes from 2 spacecraft launched in the same summer nearly 50 years ago, and both of them are running out of power in the same slow, arithmetic, unstoppable way. and 49 years is not close to enough. 49 years does not even get us to the fastest imaginable version of this journey. If we could somehow build a ship that held 1% of light speed, the crossing would still be twice as long as Voyager has been flying, and Voyager is already down to 2 working instruments. So when somebody says that interstellar travel is an engineering challenge, this is what they are actually saying, whether they know it or not. They are saying that we need to build something that stays alive at least twice as long as the longest-lived machine we have ever made, and realistically 20 or 100 or 1,000 times as long, in an environment we have only ever sampled for 5 decades. That is the first bill, and it is not really a bill for power. It is a bill for a kind of endurance that no isotope we currently know of can provide. Because the plutonium in Voyager has a very specific lifetime built into it, a number decided by physics long before the solar system existed. And when you carry that number forward, not 50 years, but 500 or 5,000, something happens to it that is genuinely difficult to believe the first time you see it written down. Picture a cylinder about the size of a coffee mug, made of a dark ceramic material, sitting inside a nest of metal casing and insulation. It is warm. Not warm like a mug of tea, warm like the ring on a stove that has just been switched off, warm enough that if you could somehow hold it, you would not hold it for long. In complete darkness it glows a dull red, faintly, all by itself, and it will do that with no fuel line, no combustion, no moving parts and no maintenance for longer than most human institutions have existed. Inside that cylinder, at this moment, something is happening a very large number of times every second. Individual atoms of plutonium are letting go. Each one spits out a small, fast particle, recoils slightly, and becomes an atom of something else, uranium as it happens. The particle travels perhaps a hair's width through the surrounding ceramic before it collides with the material and stops, and everything it was carrying turns into heat. That is all. That is the entire mechanism. Trillions of tiny impacts every second, none of them individually meaning anything, adding up to a steady warmth that never stops and never needs anything from anyone. Now stay with the cylinder and let the years run. It does not change appearance. It does not make a sound. But every year, there are slightly fewer plutonium atoms left to let go, because some of them already have. The glow is imperceptibly less. The warmth is imperceptibly less. And out on Voyager, 25 billion kilometers away, that imperceptible difference arrives at mission control as a number on a screen, and the number is 4 watts lower than it was last year, and somebody has to decide what to turn off. That is the whole shape of the first bill, and now I want to give you the actual numbers, because they are the reason the first bill cannot be paid with anything we currently have. The material in that cylinder is plutonium-238. It was chosen for deep space work for 2 good reasons. It emits almost entirely the heavy, slow kind of radiation that a few millimeters of shielding will stop completely, which makes it safe to work around. And it is extraordinarily energy-dense, about half a watt of heat from every single gram, which means a lump you could hold in 2 hands puts out as much heat as a small electric heater and keeps doing it for decades. The number that decides everything is its half-life, which is 87.7 years. That is the time it takes for half of the atoms to have decayed. It sounds generous. Nearly 90 years is longer than most people live. But watch what a half-life actually does when you run it forward, because this is where intuition fails almost everyone. After about 88 years, you have half your power. After 175 years, a quarter. After 263, an eighth. The losses do not add up, they multiply down, and multiplying down is savage. Take it to 1,000 years, which is a perfectly reasonable duration for the journey we are discussing. 1,000 years is about 11.5 half-lives. What is left, out of everything you launched with, is about 0.03%. Let me put that in real hardware. A generator that produced 470 watts on launch day, enough to run a small collection of instruments and a radio, would, after 1,000 years, be producing roughly 1/6 of a watt. That is not enough to run a wristwatch. That is not enough to blink a light-emitting diode. The spacecraft would arrive at its destination as a completely inert object, structurally intact, chemically fine, absolutely dead, carrying instruments in perfect condition that will never be switched on again. And if you take it to 10,000 years, which some proposals genuinely require, the fraction remaining has 34 zeros after the decimal point before you reach a meaningful digit. There is not a partial answer at that point. There is nothing. This is not a design flaw. You cannot engineer around it. It is not that our generators are badly built. It is that the universe has decided how long that particular arrangement of protons and neutrons is going to hold together, and the decision was made before the Earth existed. So the obvious move is to find a different isotope, and there is a real program doing exactly that, and it is genuinely promising. The European Space Agency has been funding work since 2009, alongside the United Kingdom's National Nuclear Laboratory, on generators fueled by americium-241 instead. Americium's half-life is about 432 years. That is roughly 5 times longer than plutonium. Over a 10-year mission, plutonium loses about 7.5% of its heat output. Americium loses about 1.5%. Over a 1,000-year crossing, an americium source would arrive still producing about 1/5 of what it left with, which is not comfortable, but it is not nothing either. It is the difference between a dead object and a working one. The reason Europe started that work, incidentally, was not endurance at all. It was independence. Essentially, all of the world's plutonium-238 is held by the United States and Russia, which meant that European mission planners could not commit to any deep space mission without permission from somebody else. The longer-lasting fuel was, in a sense, a political accident. But here is the trade, and it is the first appearance of a pattern that is going to repeat all night. Americium produces far less heat per kilogram. To match the output of 1 kilogram of plutonium, you need about 5 kilograms of americium. And it emits a much more penetrating kind of radiation than plutonium does, which means it needs substantially more shielding, which is more mass again. So the fuel that lasts 5 times longer arrives at the launch pad several times heavier, and mass is the one thing an interstellar mission cannot afford, because the energy required to accelerate a ship rises with the square of the speed you want and directly with the mass you are pushing. Solve the endurance problem, and you have made the propulsion problem worse. That is the shape of this. Not a wall you climb over, but a knot, where pulling any one strand tightens another. And even americium runs out. 10,000 years is 23 half-lives of americium-241, which leaves you with about 1 part in 10 million of what you started with. Every isotope we have looked at either burns bright and dies fast, or lasts long and produces too little heat to be worth carrying. Polonium-210 has a magnificent power density and a half-life of 138 days. Strontium-90 lasts about 29 years and was used in Soviet remote lighthouses, several of which were later found abandoned in the wilderness with their casings breached, which is not the most encouraging precedent for a technology whose whole premise is that nobody has to look after it. What about a nuclear reactor instead? On the face of it, this solves everything. Uranium-235 has a half-life of over 700 million years, so the fuel is simply not the constraint. But a reactor is not a lump of warm metal. A reactor is a machine. It has coolant loops and pumps and control drums and valves and sensors, and every one of those has bearings and seals and moving surfaces. Nothing of that kind has ever run unattended for a century anywhere, on Earth or off it. The last time the United States operated a fission reactor in space was 1965. And what about solar power, the way almost every satellite you have ever heard of works? Sunlight falls off with the square of distance. At the orbit of Neptune, the Sun already delivers about 1/900th of what it delivers here. At 1 light year, the figure is about 1/4 billionth. A solar array the size of a football pitch would produce less power out there than the static in an unplugged radio. There is also a supply problem that is much more ordinary and, in the short term, much more limiting. The United States stopped making plutonium-238 in the late 1980s and did not resume until 2013 at Oak Ridge National Laboratory, initially at a rate of about 50 grams a year. 50 grams. That is the weight of a small handful of coins, produced over 12 months for an entire national space program. The Department of Energy's long-term target is an average of about 1.5 kilograms a year, and progress toward it has been slow. A shipment of 550 grams in recent years was described, by the people who made it, as nearly enough to fill a coffee cup. Cassini, the mission that spent 13 years at Saturn, carried about 33 kilograms of plutonium dioxide across 3 generators. There is no version of an interstellar program that fits inside a coffee cup a year. And there is one more property of these generators that I want to plant now, because it comes back later tonight in a form nobody expects. They are astonishingly inefficient. A typical radioisotope generator converts somewhere between 4 and 7% of its heat into electricity. Everything else, 93 to 96% of it, is simply waste. New Horizons, the spacecraft that flew past Pluto, launched with a little over 200 watts of electrical output and loses about 3.5 watts a year, which means it was dumping something in the region of 4,000 watts of pure heat into the surrounding structure and out into space, continuously, from the day it launched. That heat has to go somewhere. Remember that. It becomes the third bill. None of this means the technology is fragile. If anything, the opposite is true. In 1968, a weather satellite carrying one of these generators failed on launch and dropped into the Pacific Ocean. The unit was located, recovered intact, and its fuel was reused. These things survive events that destroy everything around them. They just do not survive time. So the first bill is unpaid, and it is unpaid in a very specific way. It is not that we do not have a good enough power source. It is that no arrangement of matter that we know of produces useful electricity for as long as this journey takes, and the arrangements that come closest are too heavy to launch. But suppose you solved it. Suppose someone hands you a power supply that runs cleanly for 2,000 years at a useful output. You still have a spacecraft that has been sitting in a place with no air, no protection, and a constant sleet of high-energy particles arriving from every direction at once for 2,000 years, with nobody aboard and nobody able to reach it. And what that place does to solid matter, given enough time, is not something anybody has ever been able to measure. In a library in London, there is a set of technical papers, bound and catalogued, describing a spacecraft that was never built. The drawings show a machine over 190 meters long, a great deal of it taken up by 2 enormous spherical tanks with a wide bell at the back and, spread out around the middle, a set of thin panels far larger than the ship itself. It was designed between 1973 and 1978 by a working group of engineers and scientists at the British Interplanetary Society, most of them doing it in their evenings, and they gave it a name from Greek mythology: Project Daedalus. It was meant to go to Barnard's star, just under 6 light-years away, in about 50 years. It would have massed 54,000 tons, most of that fuel. And its designers were completely open about one thing that people usually miss when they hear about it. It had no brakes. Daedalus was a flyby. It would have crossed 6 light-years, taken photographs for a matter of hours as it swept past its target at a substantial fraction of light speed, and continued into the dark forever. Slowing down would have required as much energy as speeding up, and they could not afford it, so they did not include it. I bring up Daedalus because I promised you at the start that the engine is the part we already understand, and I want to make good on that before we go any further, so that you can stop waiting for a technological rescue that is not coming. There have been 3 or 4 serious attempts to design an interstellar drive with real numbers attached, and none of them require physics that does not exist. Project Orion, developed at General Atomics between 1958 and 1965, proposed detonating small-shaped nuclear charges behind a heavy plate and riding the shockwaves. That sounds absurd, and it is absurd, and it would probably have worked, and it is the only interstellar-capable concept ever proposed that could have been built entirely out of components that existed at the time it was drawn. It was killed by a treaty banning nuclear tests in the atmosphere and in space, signed in 1963. Daedalus and its later cousin Icarus used fusion pellets ignited by electron beams. Breakthrough Starshot, a much more recent proposal, sidesteps the fuel problem entirely by not carrying any. A gram-scale sail is pushed away from the solar system by an enormous laser array on the ground, reaching perhaps a fifth of light speed. That one has a real chance of happening eventually, and it also has no brakes, and its designers say so plainly. So the physics of pushing is fine. What it costs is simply energy, and energy is a thing you can put a number on. Here is that number, and it is worth holding on to. To accelerate 1 single kilogram of anything to 1/10 of the speed of light takes about 4.5 times 10 to the 14th joules. Translated into something you can picture, that is roughly the energy of 100 kilotons of high explosive per kilogram. So a probe weighing 1 ton, about the weight of a small car, needs the energy of 100 megatons of explosive just to get up to speed, and exactly that much again if it ever wants to stop. And the cost rises with the square of the speed. That is the cruel bit. Doubling your cruise speed does not double the bill, it quadruples it, while only halving the journey time. Which means the speed chosen in any serious study is never the fastest one achievable. It is the cheapest one that gets the mission home inside a duration the designers can defend, and every one of those durations is measured in decades at the absolute best, and centuries in every honest case. There is one fuel that would change all of this arithmetic, and it is worth mentioning only so that you know why nobody counts on it. Antimatter releases the entire rest energy of whatever it annihilates with, which makes it the most energy-dense substance the laws of physics permit. Nothing can beat it, because there is nothing left over. The difficulty is production. Every antiproton humanity has ever made was made in a particle accelerator, one at a time, at a cost in energy far greater than the energy you get back, and the total quantity produced worldwide across the entire history of the field is measured in nanograms. A nanogram is a billionth of a gram. To fuel a serious interstellar mission, you would need something in the region of a few kilograms. And at current production rates, that is not a matter of decades or centuries, but of timescales longer than the age of the universe. There is also a peculiar argument in this field that I find genuinely difficult to shake, and it is not about hardware at all. It is called the incentive trap. Suppose you launch your ship today, and it will take 1,000 years to arrive. Suppose also that propulsion technology continues to improve at any reasonable rate. Then a ship launched in 300 years will overtake yours in flight and arrive first, which means launching today wastes the money entirely. But the same argument applies in 300 years and in 600, and it never stops applying. The rational decision is always to wait, and the equilibrium is that nobody ever goes. It is not a physics problem or an engineering problem. It is a problem with the shape of the decision itself, and the only escape from it is to decide to go for reasons that are not rational at all. There is one apparent escape route, and I want to close it now so that you are not holding on to it for the rest of the night. As you approach the speed of light, distances in front of you contract, and time aboard your ship slows relative to the people you left behind. The crossing genuinely does get shorter for you. It is not a trick, and it is not a technicality. It is real, and it has been measured on particles and on atomic clocks flown in aircraft. But it is a discount that only becomes meaningful at speeds where the energy bill has already become preposterous. At 1/10 of light speed, the effect is about half of 1%, nothing. At half of light speed, you gain about 15%. You have to reach around 87% of light speed before the journey halves for you, and at that point, the energy required per kilogram is roughly 200 times what it was at 1/10. The universe does offer a shortcut. It simply prices it out of reach. So here is where we actually stand, and this is the sentence I want you to remember, because it comes back at the end of tonight in a form you will not like. The engine is the part we already understand. We know how to push. We have known for 60 years. We can write the equations, we can specify the materials, we can put a cost on it, and argue about the budget. If pushing were the only obstacle, this would be an argument about money, and arguments about money get settled eventually. What we do not know how to do is keep something alive out there. And that is not an argument about money at all. That is an absence of knowledge, and no amount of funding creates knowledge that nobody has. So the first bill was power, and it is unpaid. The second bill is the ship itself, the metal and the plastic and the silicon, the joints and the wiring and the moving parts. And I want to be honest with you about the state of the evidence here, because it is worse than the power problem in a way that is genuinely difficult to talk about. We do not know what happens to a spacecraft after 500 years in interstellar space. Not in the sense that it would be hard to calculate, in the sense that nobody has ever seen it, nobody has ever tested it, and the longest experiment ever run is currently down to 2 working instruments and losing 4 watts a year. There is an umbrella over your head at this moment that you have never seen and cannot feel. It is not the atmosphere, though that helps. It is not the Earth's magnetic field, though that helps too. It is a bubble blown outward by the sun, made of the sun's own escaping gas, and it extends past every planet, past Pluto, past the Kuiper belt, out to somewhere in the region of 120 times the distance from here to the sun. Inside that bubble, the sun's magnetic field is tangled up in the moving gas, and that tangle deflects roughly 70% of the high-energy particles that would otherwise be arriving from the rest of the galaxy. Voyager 1 crossed the outer edge of that bubble on the 25th of August, 2012. Voyager 2 crossed it on the 5th of November, 2018. And on the far side, that 70% protection is simply gone. What arrives instead are galactic cosmic rays, the bare nuclei of atoms, everything from single protons up to iron, accelerated by the shock fronts of supernovae that exploded long ago and far away, moving at a substantial fraction of light speed. They arrive from every direction, all the time, forever. There is no shielded side. There is no night. And a spacecraft crossing interstellar space is sitting in that sleet for the entire journey with no umbrella at all. What that does to a solid object is not dramatic. It is worse than dramatic. It is cumulative. When one of those nuclei passes through a piece of metal, it occasionally strikes an atom in the crystal lattice, hard enough to knock it clean out of position. That leaves a hole where an atom used to be, and puts an atom somewhere it does not belong. Individually, this is nothing. Repeated over decades and centuries, those defects accumulate, and they pin the internal planes of the metal in place so that they can no longer slide past one another. The practical consequence is that the metal gets harder and it gets more brittle. It stops bending and starts breaking. A structural member that was designed to flex slightly under load becomes, over enough time, a thing that cracks instead. Plastics have a different and equally unpleasant response. A polymer is a long chain of repeated molecular units, and its flexibility comes from the length of those chains. High-energy particles cut them. This is called chain scission, and its effect on a spacecraft is not abstract at all. The insulation on wiring gradually loses its flexibility and begins to craze and crack. Adhesives lose their grip, seals harden. Anything soft slowly becomes something that is no longer soft. On Earth, you have watched this happen. It is the same process that makes an old rubber band snap when you stretch it, or an old plastic garden chair shatter instead of flexing. It just happens out there without sunlight, and it never stops. And then there is the electronics, which is where it becomes genuinely strange. When a heavy nucleus passes through a semiconductor, it leaves a trail of electrical charge behind it. Some of that charge gets trapped in the insulating oxide layers inside the device, and it stays there, shifting the voltage at which each transistor switches on. Over a long enough time, the whole circuit drifts away from the conditions it was designed for, and one day, something that has always worked simply does not. That is the slow version. The fast version is that a single particle striking a single memory cell can flip a 1 into a 0, or a 0 into a 1, in an instant, with no warning and no pattern. Sometimes that corrupts a number. Sometimes it corrupts an instruction. And occasionally, it puts a circuit into a state where it draws current continuously until the power is cycled, which on a spacecraft with nobody aboard means until an automated system notices, if there is one, and if it is still working. Here is the part that inverts what most people assume. Modern electronics are far more vulnerable to this than old electronics, not less. As chips have shrunk, the amount of electrical charge that represents a single 1 or 0 has shrunk with it, which means a smaller disturbance is enough to flip it. Voyager's entire computer memory is about 69.5 kilobytes, built with features enormous by today's standards, and part of the reason it is still functioning after 49 years is precisely that it is crude. Radiation-hardened processors flown today typically run 1 to 2 decades behind commercial parts in raw capability. That is a permanent tax, paid in performance, in exchange for not dying. Now set the radiation aside, because the vacuum itself does 2 things that nobody expects. The first is that solid materials evaporate. In a hard enough vacuum, with nothing pressing back, atoms at a surface simply leave, one at a time, and never return. Over decades, this is measurable. Lubricating oils are gone. The plasticizers that keep flexible materials flexible are gone. Certain alloying elements migrate out of the metals that contain them. This is why spacecraft mechanisms do not use oil at all, but instead use dry, solid coatings, materials like molybdenum disulfide, which work well and which wear away with use and are never replenished. Every mechanism on a spacecraft has a finite number of movements designed into it from the beginning. Not an estimate, a budget. The second thing is stranger, and I find it the most quietly unsettling fact in this whole part of the subject. It is called cold welding. On Earth, every metal surface you have ever touched is covered. There is a layer of oxide, formed the instant the metal met the air, and on top of that, a film of adsorbed gas and water and grease. Two pieces of metal pressed together are never actually touching each other. They are touching through all of that. In deep space, over enough time, the oxide is eroded away by the particle environment, and there is no air to reform it. And when two clean metal surfaces of the same material come into contact under those conditions, the atoms on either side genuinely cannot tell which piece they belong to. The lattice simply continues across the join. The two parts become one part. No heat, no welder, no process, just contact. Which means a hinge can stop being a hinge. A latch can stop being a latch. A mechanism designed to move can quietly become a solid object while nobody is watching, and the first anyone knows about it is that a command is sent and nothing happens. There is a real flight example of what lubricant loss and sticking parts can do to a mission, and it is one of the saddest stories in planetary exploration. Galileo launched toward Jupiter in 1989, and in 1991 it was commanded to open its main high-gain antenna, which was folded up like an umbrella for launch. It did not open. Several of the ribs stuck in their sockets. The failure was attributed to lubricant lost during years of storage and repeated transport across the country before launch. Engineers tried for months. They warmed the spacecraft, they cooled it, they hammered the deployment motor on and off nearly 500,000 times. It never opened. Galileo completed its entire mission through its tiny backup antenna, at a data rate a small fraction of what had been planned, with the ground team rewriting its onboard software from 100 million kilometers away to compress everything it sent. The mission was a triumph, and it was also permanently crippled, and the cause was not radiation, or a collision, or an explosion. The cause was that some grease had slowly gone away. There are 3 more mechanisms on this list, and I will keep them brief, but I do not want to leave them out, because the whole point of the second bill is that it is not one problem. It is a dozen small ones, all running at once, none of them fixable. Metals under sustained load slowly deform. This is called creep, and it happens even at low temperatures given enough time. A strut held in tension for 1,000 years is not quite the same shape at the end as it was at the beginning, and a structure whose parts have all quietly changed shape by a fraction of a millimeter is a structure whose alignments no longer hold. Optical instruments in particular care about that a great deal. Thermal cycling works joints loose. Even in interstellar space, a spacecraft that rotates has a face turning toward whatever heat sources exist and away again, and its own internal heat rises and falls as systems switch on and off. Different materials expand by different amounts when warmed. Over enough cycles, that difference flexes solder connections and bolted joints until they fail, and solder joints and cable connectors are historically among the most common long-term failure points in spacecraft. They are also the parts least helped by carrying spares, because a spare connector still has to be connected by somebody. And then there is the dust. Interstellar space contains a very thin scattering of solid grains, most of them far smaller than a grain of sand. At normal speeds, they are nothing. At cruise speeds, they are not. A single grain weighing 1 milligram, call it a large speck, something you would brush off a sleeve without noticing, arriving at a fifth of the speed of light, carries about 1 billion joules of energy. That is roughly the energy of half a ton of high explosive, delivered to a point on the hull the size of a full stop. And over 1,000 years, the chance of meeting one stops being small. The standard answer to all of this is redundancy. Carry 2 of everything, or 3. Carry spares. Build in the ability to reroute around failures. And that genuinely does work, up to a point. Juno, the spacecraft currently orbiting Jupiter inside the most punishing radiation environment in the solar system, carries a vault made of titanium, with walls about 1 centimeter thick, weighing somewhere between about 170 and 200 kilograms, whose entire purpose is to sit around the electronics and absorb what would otherwise destroy them. That is a fifth of a ton of mass launched from Earth, at enormous expense, that does nothing at all except not die. But redundancy has a ceiling, and the ceiling is this: the spare parts age at exactly the same rate as the parts they are meant to replace. A backup computer that has been sitting in the same particle sleet for 800 years has accumulated the same damage as the primary. Carrying 2 of something protects you against bad luck. It does not protect you against time, because time is happening to both of them. That is the second bill. And I would love to tell you what it comes to over 1,000 years. But I cannot, and neither can anybody else, and the reason why is the most honest and most uncomfortable thing in this entire subject. On a flat grey plain on the moon, in a place called the Sea of Tranquility, there is a small panel about the size of a laptop, lying on the surface where 2 men set it down on the 21st of July, 1969. It is covered in 100 little cubes of fused silica, each cut so that any light entering it comes straight back out the way it came, no matter what angle it arrived from. There is no power supply. There are no electronics. There is nothing on it that moves. And it still works. Observatories on Earth still fire laser pulses at that panel and still catch the return, 57 years later, and from the timing of that return, we know the distance to the moon to within a few centimeters. It is, as far as anyone can tell, the longest functioning object humans have ever placed anywhere off this planet, and it will probably still be working in 10,000 years. Now notice why. It works because it does nothing. It has no fuel to run out of, no circuits to corrupt, no bearings to seize, no lubricant to lose. It is a shape. A shape does not decay in any way that matters, and that is the entire trick. This is the uncomfortable relationship at the heart of the second bill, and I want to state it plainly. Longevity and capability appear to be opposed. The most durable thing we have ever made off-world is also the least capable thing we have ever made off-world. Everything we would want a starship to do, measure, decide, transmit, adjust, survive, requires the exact kinds of components that do not last. And here is the sentence that I think is the single most honest thing in this entire subject, and it is almost never said out loud. We have no idea what happens to a spacecraft after 50 years in interstellar space, because nothing has ever been there longer. That is not a figure of speech. There is no data set. There is no long-duration materials qualification program for this environment, because such a program would require putting samples out there and waiting, and the waiting is the thing being tested. Every laboratory simulation is an accelerated one, which means bombarding a sample intensely for a short time and assuming the damage adds up the same way it would over centuries at low intensity. Sometimes it does. Sometimes it very much does not, because slow damage allows time for defects to migrate and partially heal, and fast damage does not. Nobody can tell you with confidence which category any given alloy falls into over 1,000 years, because the experiment has never been performed and cannot be performed inside the working life of the person who would have to run it. So when you read that a proposed interstellar probe would function for 1,000 years, understand exactly what kind of claim that is. It is an extrapolation of a factor of 20 beyond the longest experiment ever conducted. 20 times. If someone tested a bridge design for 1 year and then certified it for 20, you would want a word with them. And the experiment we are extrapolating from is not even finished. It is still running, tonight, on a spacecraft that is down to 2 working instruments and losing 4 watts a year. I want to give you one moment from that experiment, because it shows both how well this can go and how thin the margin actually is. In November of 2023, Voyager 1 started sending nonsense. The engineering data and the science data stopped being data at all and became a repeating pattern of ones and zeros that meant nothing. The spacecraft was clearly alive. The carrier signal was there. It was responding to commands in the sense that something was changing, but it had lost the ability to say anything intelligible. From 24 billion kilometers away, with every command taking nearly a full day to arrive and every reply taking nearly a full day to come back, a team on Earth had to work out what had gone wrong inside a computer designed in the early 1970s. It took them 5 months. What they eventually established was that a single chip holding a portion of the software that packages up the spacecraft's data for transmission, had stopped working. Possibly a particle strike. Possibly just 50 years of age. The memory it held was simply gone, and there was no way to repair it and no way to replace it. So they did the only thing left. They found unused pockets of memory elsewhere in the system, divided the affected code into pieces small enough to fit into those gaps, rewrote every internal reference so that the pieces would still find each other, and sent the whole thing up. In April of 2024, Voyager 1 started making sense again. That is an extraordinary piece of work. It is also completely dependent on something that will not exist on a 1,000-year mission. It worked because there were people on Earth who understood a 50-year-old computer architecture well enough to perform surgery on it blind, from a day away, with 1 attempt. Some of those people had worked on the mission for decades. The knowledge was in human heads. Now imagine the same failure at year 600 of a 1,000-year crossing. There is nobody who designed the system. There is nobody who has ever seen the system. There is very likely nobody who reads the language its documentation was written in. The proposed answer to that is a spacecraft that repairs itself, a machine carrying the tools, the raw material, and the intelligence to diagnose its own failures and rebuild its own components. And I want to be careful here, because this is not a stupid idea. It is the only idea with a high enough ceiling to actually work. But notice what it does. It does not remove the problem. It moves it. Now you need a repair system that functions for 1,000 years, and a repair system is a machine, made of the same metals and plastics and semiconductors, sitting in the same particle sleet, with the same bearings and the same lubricants, and the same memory chips. The thing that fixes everything else has to be the one thing that never breaks, and nothing we know how to build has that property. I want to slow down here for a moment, because I think this is the part of tonight that deserves it most, and it is not the part with the biggest numbers in it. We are used to hearing that things are hard. Interstellar travel is hard. Building a fusion reactor is hard. Curing a disease is hard. Hard is a comfortable word, because hard implies that the difficulty is on our side of the problem, and that effort is the currency that buys it down. Hard means try harder. This is not that. What we have just described is not a hard problem. It is an absence of evidence. Nobody is telling you that a 1,000-year spacecraft is difficult to build. They are telling you that nobody knows whether it is possible, because the only way to find out takes longer than any of the people asking will be alive. We are in the position of someone who has been given a substance and asked whether it will still be intact in 1,000 years, and whose only honest answer is, "Ask me in 1,000 years." And every single approach to closing that gap has the same shape. Run the experiment and wait. Which means the first genuine answer to the second bill will arrive long after everybody who cares about it tonight is gone, and will be delivered to people who did not ask the question. We are 2 bills in. Power that runs out and matter that will not hold. And so far, both of them have at least been arguments about things, about isotopes and alloys and grease. The third bill is not about a thing at all. It is about a law, and unlike the first 2, this one cannot be negotiated with, cannot be improved by better engineering, and applies exactly as hard to a civilization 1 billion years ahead of us as it does to us. And it has a consequence that reaches far outside this subject, into a question people have been asking about the sky for a very long time. Put your hand flat on a table in front of you for a moment. Feel the surface. If it is wood or stone, it feels cool, and that coolness is not a property of the table. It is heat leaving your hand and going into the table, atom bumping into atom all the way down. That is conduction. Now, let your hand rest an inch above a mug of tea and feel the warmth rising past it. That is convection, warm air carrying energy upward and away. Both of those require something to be there. Conduction needs matter touching matter. Convection needs a fluid that can move. In space, there is neither. A spacecraft is not touching anything, and there is nothing around it to circulate. Which leaves exactly one way for it to get rid of energy, and only one, and it is the one that never occurs to anybody. It has to glow. Everything with a temperature radiates. You are doing it right now, in the infrared, at a rate of about 100 watts, which is why a thermal camera can see you in the dark, and why a room full of people gets warm. In a spacecraft, this is not a curiosity, it is the only exit. Every joule of energy generated on board, by the power system, by the electronics, by the propulsion, by the crew if there is one, must eventually leave as light. If it cannot leave as light, it stays, and the temperature climbs until something stops working. This is governed by a relationship discovered in the 1870s, and it has a shape that is both extremely generous and extremely cruel. The power a surface radiates goes up with the 4th power of its temperature. Not double the temperature for double the output, double the temperature for 16 times the output. The generous half of that is that hot things dump heat beautifully. If you can run a radiator glowing at 800 degrees, it sheds energy at a furious rate from a small area. The cruel half is that you can only dump heat into something colder than the source. You cannot cool a delicate instrument that needs to sit at room temperature using a panel running at 800 degrees, any more than you can cool a drink with a hot water bottle. And the moment you drop your radiator down to a temperature that is actually useful for electronics and for people, that 4th power turns around and works against you. Here are the numbers. A perfect radiating surface at 300 Kelvin, roughly ordinary room temperature, sheds about 460 watts for every square meter of it. And that is the idealized figure, before you account for the fact that real materials are imperfect, that a folded radiator sees parts of itself and reabsorbs its own output, and that the panel is also catching heat radiating off the ship it is attached to. 460 watts per square meter. Put that against the power a real starship would be running. Any propulsion system capable of pushing a serious payload to even 1% of light speed in a reasonable time is operating in the gigawatt range. A gigawatt is roughly the output of a large power station, the sort that supplies a city. Suppose your engine is remarkably efficient, and only 1% of that ends up as waste heat that has to be shed at ordinary temperatures. 1% of a gigawatt is 10 megawatts. Divide 10 million watts by 460 watts per square meter, and you get about 20,000 square meters of radiator. 20,000 square meters is a square roughly 140 meters on each side. Two of them, one on either side of the ship, would be 400 meters of thin panel spread across the dark. For comparison, the International Space Station, the largest structure human beings have ever assembled in orbit, is about 109 meters along its longest dimension, and its entire thermal control system is built to handle somewhere in the region of 70 kilowatts. Not 10 megawatts. 70 kilowatts. We would need to handle more than 100 times that, using a structure many times larger than anything we have ever put together off the ground, and it would have to survive everything we discussed in the last part for the entire journey. This is why, if you look carefully at the drawings of any serious interstellar design, the ship is mostly not ship. Daedalus is mostly tanks and panels. Every honest concept ends up looking less like a rocket and more like a set of enormous thin wings with something small in the middle. I want you to actually see it, so let me put you outside for a moment. You are floating, at a distance, in absolute darkness. There is no up. The sun is behind you somewhere, one bright point among many, no longer meaningfully different from any other star. In front of you is the ship, and the hull of it is essentially invisible, cold, dark, matte, nothing reflecting off it because there is nothing to reflect. But the radiators are not invisible. They stretch out on either side, far wider than the ship is long, thin as paper by comparison with their extent, and they are glowing. Not brightly. A dull, even red, like the last of a fire an hour after everyone has gone to bed, spread across an area larger than a city block. There is no flicker. There is no sound. There is nothing dramatic happening at all. It is simply the ship's waste, pouring out into the dark at 460 watts a square meter, silently, continuously, and it will not stop for the entire crossing. Whatever is happening inside, instruments running, computers thinking, an engine holding a thrust it will hold for years, arrives out here as a faint red warmth that nothing will ever feel. And then the inversion, which I think is the loveliest fact in this entire subject. If a starship must glow, then a starship can be seen. Not by looking for it directly, and not in visible light. But an object radiating megawatts in the infrared is, in principle, detectable across interstellar distances by an instrument built to notice it. Thermodynamics does not permit stealth over long baselines. Anything doing serious amounts of work has to dump the waste somewhere, and the only somewhere available is outward, in every direction, forever. That is not a thought experiment. There is a whole branch of the search for life elsewhere that works on exactly this principle, not listening for signals at all, but surveying tens of thousands of galaxies looking for anomalous infrared excess, the fingerprint of energy being used on a large scale. If a civilization somewhere had solved the 4 bills we are working through tonight and was actually moving mass between stars at scale, it should be glowing in a way we could catch. Those surveys have run. They have not found an unambiguous candidate. And that null result means one of two things, both of which are interesting. Either such engineering is far rarer than we assume, or our assumptions about what it would look like are wrong. There are a few more things about heat worth knowing, and they run in different directions, which I like. The first is that one part of this problem has an unusually good solution, and it is one of the very few subsystems on a starship that might genuinely survive 1,000 years. It is called a heat pipe, and it is a sealed tube with a small amount of liquid inside. At the hot end, the liquid evaporates, taking energy with it. The vapor drifts to the cold end, condenses, and gives that energy up. Then the liquid wicks back along the inside of the tube to the hot end, and does it again. There is no pump. There is no fan. There is nothing that turns or slides. It is a heat engine with no moving parts at all, and spacecraft are full of them. Its one long-term failure mode is that the working fluid very slowly breaks down chemically and produces gases that will not condense, which gather at the cold end and gradually choke the tube. Even that takes a long time. If you were looking for a component to bet on for a millennium, this is the one. The second thing is that some designers have proposed abandoning solid radiators entirely because panels are heavy and fragile. The alternative is to spray your coolant directly into space as a fine mist, let the droplets glow and cool as they fly across a gap, and catch them again on the far side. It gives you an enormous radiating area for almost no mass, and it has been studied seriously since the 1980s. The unsolved part is that some of the droplets miss the collector, and a coolant you keep losing is a fuel tank with a hole in it by another name. The third thing is that a crewed ship has a flaw it can never get under. A resting human being produces about 100 watts of heat, continuously, awake or asleep, for their entire life. A crew of 20 is 2 kilowatts that exists whether or not the engines are running, whether or not the instruments are on, whether or not anybody is doing anything. You cannot switch people off to save power. They are, thermally speaking, a small permanent fire that you are obliged to carry. And the last thing is the floor underneath everything. The universe itself has a background temperature, the faint, even glow left over from its first few 100,000 years, sitting at about 2.7 degrees above absolute zero. Nothing anywhere, no matter how clever, can passively radiate below that. That is the coldest a thing is allowed to be by simply being left alone. It is not a limitation anyone will ever run into on a starship. I mention it because I find it quietly remarkable that the entire universe has a lowest setting, and everything in it, including your ship and including you, is sitting somewhere above it. Let me stop here for a moment and put the 3 bills together, because we are halfway, and it is worth seeing them stacked before the last one arrives. Bill 1 is power, and it fails because every isotope we know either dies too fast or produces too little, and the one that lasts longest arrives 5 times heavier. Bill 2 is matter, and it fails because the environment slowly hardens metal, cracks plastic, corrupts memory, evaporates lubricant, and fuses moving parts together, and because nobody has ever measured any of that beyond 50 years, so every long-duration claim is a guess wearing a number. Bill 3 is heat, and it fails not because of any material or any isotope, but because of a law, which says the only exit is to glow, and glowing at a useful temperature requires a structure larger than anything we have ever built. 3 bills, and every one of them makes another one worse. Longer-lasting fuel is heavier. Heavier ships need more energy. More energy makes more heat. More heat needs more radiator. More radiator is more mass to keep intact for 1,000 years. in the environment that destroys things. That is 3. And they are all, in the end, problems about objects, which means they are at least the kind of problem an engineer can be handed. The 4th is not. In the Mojave Desert in California, in a valley of dry hills, there is a dish 70 meters across, standing in the open air. It is white. It is enormous, wider than the wingspan of the largest passenger aircraft ever built, and it turns. Slowly, on bearings floating on a film of oil, it swings around and tips its face to a particular patch of sky and holds there, and it does that because a computer somewhere holds a schedule, and the schedule says that at this hour, this dish belongs to this spacecraft. There are 3 sites like it. Goldstone in California, a site outside Madrid in Spain, and one outside Canberra in Australia, spaced roughly a third of the way around the planet from each other, so that as the Earth turns, something is always facing outward. Together, they are called the Deep Space Network, and everything humanity has ever sent beyond the Moon talks through them. Every image from Mars, every measurement from Jupiter, every remaining word from Voyager. The Deep Space Network was established in 1963. It is 63 years old. NASA itself is 68, founded in 1958. The European Space Agency is 51, founded in 1975. Hold those numbers, because we are about to put them next to something. Suppose everything else goes perfectly. Suppose someone solves the isotope problem and the materials problem and the heat problem, and a ship departs, and it works. It crosses 1 light-year over some number of centuries, in perfect condition, with an instrument suite that still functions, and at the end of it, it does what it was built to do. It turns its antenna back toward the sun, and it transmits. The signal takes a year to arrive. And then it needs somebody here to catch it. Not a species, not a civilization in the abstract. A specific organization with a specific budget line that still owns a working dish, still has a receiver tuned to the right frequency, still possesses the software or the knowledge to turn that stream of ones and zeros back into something meaningful, and still has a person whose actual job on a Tuesday morning is to look at the output. That organization has to have existed continuously and remained competent, and considered this worth paying for the entire duration of the journey. Now put the numbers side by side. We are asking for institutional continuity across 1,000 years from an organization type that has existed for less than 70. And look at what the record actually is for human institutions of any kind. The University of Bologna has been running since around 1088, 938 years. The Icelandic Parliament, the Althing, is traditionally dated to 930. There are religious institutions with continuous lines considerably longer. And the outer edge, the case people always reach for, is a Japanese company called Kongo Gumi, founded in 578 to build a Buddhist temple, which went on constructing and maintaining temples as an independent family business for more than 1,400 years, before it was finally absorbed by a larger firm in 2006. So a 1,000-year mission is asking for something at roughly the level of the oldest university on Earth. Not the oldest space agency, there are none of those. The oldest university. A thing that has survived wars, plagues, revolutions, changes of language, changes of religion, the invention and collapse of entire economic systems, and simply kept doing what it does. And it has to survive all of that while doing something with no visible return. A university teaches people continuously. You can see the point of it every year. A temple company builds temples. There is a temple. What does a mission control organization for a 1,000-year probe deliver, in year 400, to justify its funding? Nothing. It delivers a confirmation that the spacecraft is still there, if that, and a promise. For 400 consecutive years of budget meetings, there is a physical reason this cannot be softened too, and it is worth a moment. Radio signals fall off with the square of distance. At 1 light-year, a transmitter is about 372 times further away than Voyager 1 is right now. Square that, and the received power is roughly 138,000th of what we currently get from Voyager, and what we currently get from Voyager is already so faint that catching it requires the largest dishes on Earth pointed at it deliberately. So the antenna at this end of a 1 light-year mission cannot be a modest thing quietly maintained by 2 enthusiasts. It has to be extraordinary. Somebody has to have built it, and somebody has to keep paying to keep it standing and turning and pointed at the right patch of sky, for centuries, for a message that has not arrived yet and might not. And that dish is not a monument. It is a machine, and it needs looking after in the most ordinary way imaginable. A 70-meter antenna is hundreds of tons of steel riding on bearings that float on a thin film of pressurized oil, and it has to be greased and repaired and periodically taken apart and rebuilt. The Goldstone antenna has been through several major refurbishments in its lifetime, each one taking it out of service for months. During those months, everything that talks through it has to be handled by something else or simply not heard from at all. And there is not much slack in the system. The Deep Space Network has been oversubscribed for years. There are more missions wanting time than there are hours of dish availability, and every hour is fought over. Voyager, the most distant thing we have, gets a small and shrinking share, because it is old, and because newer missions produce more data that more people are waiting for. That is not anybody behaving badly. That is what finite resources look like. But it means the listening end is already a scarce commodity today, in a decade when interest is high and the mission is famous. Nobody has ever had to defend a listening budget across 4 centuries of changing priorities, because nobody has ever had a mission that lasted that long. Notice also that conversation, in the ordinary sense, is finished. At 1 light-year, you send a question and the answer comes back 2 years later. 10 exchanges is 20 years. A single misunderstanding costs you 2 years to clear up. There is no operator watching a screen and reacting. There is a message being sent into the future and a reply arriving from the past, and every person in that loop is dealing with a version of the spacecraft and of themselves that no longer exists. Most mission proposals in this field handle all of this with a single sentence, and it is worth noticing what the sentence does. It says, in effect, that a civilization capable of launching such a probe will obviously still be capable of receiving it. And that is not a plan. That is an assumption, and it is the single largest unexamined premise in the entire field. It assumes that capability, once acquired, stays. History does not support that at all. There are technologies humanity has had and lost, sometimes for centuries, techniques of construction, of navigation, of metallurgy, held by a few people, written down badly or not at all, and gone within a generation when the conditions that supported them changed. And even if all of that holds, there is a subtler failure waiting, which is that the message might arrive perfectly and be unreadable. Data formats rot far faster than institutions do. This has happened to NASA already, repeatedly, over timescales of mere decades. The data from the Viking landers, which touched down on Mars in 1976, ended up on magnetic tapes in formats that nobody could read, written by software whose authors had retired or died. Recovering it in the 1990s took a genuine rescue effort, finding surviving drives, reverse engineering the encoding, reconstructing what the numbers had meant. 20 years, and the meaning had already started to slip away inside the same organization that created it, with most of the original people still alive. The team that built the Voyager Golden Record understood this better than almost anybody. That is why the record is a physical analog disc rather than any digital format, and why the instructions for playing it are etched on the cover as pictures rather than written in any language. They assumed no shared format, no shared institution, no shared alphabet. They assumed the finder would have nothing in common with them at all. That assumption turns out to have been reached independently and much more rigorously by a completely different group of people working on a completely different problem, a problem with the same 10,000-year horizon and no spacecraft in it at all. They were not trying to send a message to the stars. They were trying to send one to the future about something buried in the New Mexico desert. And what they concluded after years of work is the most sobering document I have ever read on the question of whether human attention can be made to last. 40 kilometers east of Carlsbad, New Mexico, there is a stretch of scrub desert with a few low buildings on it and a shaft going down. The shaft descends 650 meters through rock into a bed of salt that was laid down when a shallow sea dried up about 250 million years ago. Down there, in tunnels cut into the salt, sit drums of clothing, tools, gloves, rags and equipment contaminated with plutonium and other transuranic elements from decades of American nuclear weapons work. The salt is the point. Salt beds flow very slowly under their own weight. Over centuries, the tunnels will close around the drums and seal them into solid rock, which is exactly what is wanted. The site is called the Waste Isolation Pilot Plant, and it began accepting waste in 1999. And in 1993, 6 years before it opened, a group of people were given one of the strangest engineering assignments in history. The regulation was straightforward on its face. The site had to be marked in a way that would keep human beings from accidentally digging into it for 10,000 years. 10,000 years. Read that again as a span of time, rather than as a number. 10,000 years ago, the last ice age had recently ended. Agriculture was just beginning. There was no writing anywhere on Earth. Every city you have ever heard of was thousands of years from being founded. The task, then, was to communicate a specific and urgent warning to somebody at the far end of a gap, as long as the whole of recorded history, and then some, with no possibility of a reply, and no way to check whether it had worked. Sandia National Laboratories convened panels of experts to work out how. Anthropologists, linguists, archaeologists, materials scientists, astronomers, science fiction writers, and they produced a report with what may be the least dramatic title ever attached to the most unsettling content: Expert Judgment on Markers to Deter Inadvertent Human Intrusion into the Waste Isolation Pilot Plant. I want to walk you through what they concluded, one piece at a time, because each conclusion is a wall, and each wall is exactly the wall a 1,000-year spacecraft runs into. They started with language, and language failed immediately. English as a written thing is about 1,500 years old, and its earliest form is completely unreadable to an ordinary speaker today. Not difficult, not archaic, unreadable, a foreign language wearing familiar letters. Go back 3,000 years anywhere, and you are into scripts that took teams of scholars generations to decipher, some of which have never been deciphered at all. There is no writing system on Earth that is confidently 10,000 years old, because writing itself is not that old. Whatever you carve, the words will not survive the distance. So the panels recommended carving the warning in many languages at once, and simply accepting that most or all of them would be dead. Then they tried symbols, and symbols failed for a more interesting reason. Symbols do not merely fade, they invert. The skull and crossbones has meant poison, and it has meant piracy, and in some periods and places it has meant resurrection and the promise of life after death. A symbol is a convention, and conventions turn over. There is no image you can carve that is guaranteed to mean danger rather than treasure, and a marker that reads as treasure is worse than no marker at all. It is an advertisement. Then they considered simply maintaining the site. Postcards. Keep records. Have an organization that knows what is there and passes the knowledge on. And this failed on the plainest possible grounds, which is that no institution in human history has ever lasted 10,000 years, and the panels were not willing to bet the health of people 10,000 years from now on the first one that does. So they were left with the only thing that might not depend on language, symbol, or institution, physical form. Shapes that feel wrong before they are understood. The designs they proposed are genuinely strange to read about. Fields of enormous concrete spikes at broken, disordered angles. Earthworks arranged to be uncomfortable to cross. Great blocks of stone laid out to feel abandoned rather than honored, hostile rather than grand. Architecture as a scream. And then, in the hope that some part of it might survive translation, they wrote the words anyway. And what they wrote is not like anything else in the history of monuments. Let me put you there. You have walked across a great deal of desert to get to this place, and for the last hour you have been able to see that something is ahead. Not a ruin. Ruins look like something that fell down. This looks like something that was made to look like this. As you get closer, the shapes resolve into concrete, dozens of columns as tall as trees, leaning at angles that do not agree with each other, casting a mess of shadows across ground that has been deliberately raised into a low mound around them. Nothing here is beautiful. Nothing is even symmetrical. It has been arranged, with obvious effort and enormous expense, to make a person feel that they have arrived somewhere they should not be. There is writing. It appears in many scripts, most of which you cannot identify at all, on granite faces set into the stone. And one of them, by luck, is close enough to something you can read that you can pick your way through it. It says, "This place is not a place of honor. No highly esteemed deed is commemorated here. Nothing valued is here. This place is a message and part of a system of messages. Pay attention to it. Every monument you have ever seen was built to say the opposite. Something important happened here. Someone worth remembering is here. Come closer. This is the only structure our species has ever seriously designed to say, we made this, we meant it, and the meaning is, go away. That is the most serious attempt human beings have ever made to talk across 10,000 years. It is funded, it is documented, it is government commissioned, and it is the only one of its kind. And its conclusion, stripped of the engineering language, is this: we do not know how to do it. Every mechanism a person would naturally reach for fails, and the best we can manage is to build something so unpleasant that a stranger's instincts might do the work our words cannot. The panels also thought carefully about how much a message could hope to carry, and they arrived at a structure of levels that I think is quietly brilliant. The simplest level says only, something made by human beings is here. That much might survive on shape alone. The next level says, this is dangerous. The next explains what the danger is and where it sits. And the most detailed level, the one that explains why and what was done and by whom, is the one nobody expects to survive at all. You design so that if only the first level gets through, the message has still done something. It is a warning, built in layers, on the assumption that most of the layers will be stripped away by time. Other proposals from this same field of study, and they are real, published proposals, not jokes, though some of them read like jokes, went further. One suggested creating a self-perpetuating priesthood, an order whose entire function would be to preserve the knowledge of what is buried where and pass it down through ritual, on the reasoning that religions have demonstrably outlived every other kind of human organization. Another proposed breeding cats that visibly change color in the presence of radiation and seeding folklore and songs about them into the culture, so that thousands of years later, long after anyone understood why, people would still know that when the cat changes color, you leave. Both ideas are attempts to solve exactly the same problem. How do you store a fact in a species rather than in a document? And there is a cautionary example sitting in the British Museum that puts all of this in perspective. Egyptian hieroglyphs were carved on monuments explicitly built to last forever, by a civilization that endured for thousands of years and thought hard about permanence. The ability to read them was completely lost. For roughly 1400 years, nobody on Earth could understand a word of it. The writing survived beautifully, the meaning did not. And what eventually brought it back was not any plan or any institution. It was a broken slab of stone that happened to carry the same text in 3 scripts, which happened to be reused as building material, which happened to be buried, and which happened to be found by accident by soldiers digging a fort in 1799. The most famous message ever recovered from the remote past was recovered by luck. That is the actual track record. Now bring that back to the ship. The starship problem is the same problem with one additional requirement that makes it far harder. WIP only needs the future to understand a warning and then leave. It needs one moment of comprehension, followed by absence. A 1 light-year mission needs the opposite. It needs the future to be present and competent and equipped and paying attention. It needs someone at the far end of the gap not merely to understand, but to have a working dish, a working receiver, the right frequency, the right decoder, and the decision, made freshly, that morning, by a person with other things to do, to point it at an empty patch of sky and wait. We do not know how to send a warning across 10,000 years. What we would need to send is an appointment. And an appointment is a much more demanding thing than a warning, because a warning only has to be received once, by anyone, in any condition. An appointment has to be kept. It requires the other party to have survived, to still have the equipment, to still know what the equipment is for, and to have decided that showing up is worth their time. A warning can be shouted into the dark, and still count as a success if a single stranger flinches. An appointment fails completely unless somebody is standing in the right place at the right moment, deliberately, having chosen to be there. And yet, and this is where I want to leave the heavy part of tonight behind, human beings do keep trying. Not on that scale, and not with that seriousness, but there are small experiments in deliberate lasting scattered around the world right now, some of them decades old, one of them nearly 2 centuries. They are modest and slightly eccentric and completely sincere, and they are the only real evidence we have about whether attention can be handed from one generation to the next at all. In a corridor in the Clarendon Laboratory in Oxford, inside a glass case that nobody is allowed to open, there is a small brass bell with a metal sphere hanging beside it. The sphere is about 4 millimeters across, and it is swinging. It swings from one side to the other, touches one bell, swings back, touches the other. It does this roughly 2 times every second. It has been doing it since about 1840. Nobody knows exactly what is inside the two dry batteries driving it, because opening them to find out would end the experiment, and nobody is willing to be the person who ended it. The best guess is a stack of thousands of alternating metal and paper discs coated with something like manganese dioxide, sealed in molten sulfur. Whatever is in there, it has been pushing that little sphere back and forth for 186 years. 9 or 10 billion swings, give or take. And here is the sentence that matters for tonight. As far as anybody can determine, that is the longest continuous operation of any powered device in the history of the human species. 186 years. Not 1,000. Not 5,000. 186, and it is a bell in a case doing the simplest possible thing in a heated building, watched over by an institution that has existed for 9 centuries. That is the record. I wanted you to have the actual record, because after the last part, it is easy to think of the 4th bill as an abstraction, and it is not. It is a number, and the number is small. There are a handful of other deliberate experiments in lasting, and I find them genuinely moving, so I want to spend a little time here. Inside a mountain in a remote part of West Texas, an organization called the Long Now Foundation has been building a clock. It is a mechanical clock, cut from stainless steel and titanium and ceramic, hundreds of feet tall, designed to keep time for 10,000 years. It ticks once a year. Its century hand advances once every 100 years. A cuckoo emerges once a millennium. It is powered by the daily change in temperature between the mountain's day and night, and by anyone who walks in and winds it. There is a chime generator inside it, built to ring a different sequence of bells every single day for 10,000 years without repeating. The foundation was started in 1996 with the explicit aim of encouraging people to think on longer timescales than a financial quarter. The clock has been under construction for decades. It is not finished. In the Arctic, on the island of Spitsbergen, there is a concrete wedge sticking out of a snowfield, with a tunnel behind it running 100 meters into the side of a mountain. Inside are vaults holding hundreds of thousands of varieties of crop seeds, sent from gene banks all over the world, stored at -18 degrees. The site was chosen because the permafrost would keep the seeds cold even if the refrigeration failed entirely and everyone went away. The Svalbard Global Seed Vault opened in 2008, and it is intended to last centuries. In 2016, meltwater from unusually warm weather got into the entrance tunnel and froze. The seeds were never at risk, but the incident meant something all the same. The vault was placed where it was because the climate there was reliable, and within 8 years the climate there had changed. Every long-duration plan contains an assumption about the world staying broadly the same, and that is the assumption that tends to go first. And then there is my favorite, because it is the one with people in it. In 1927, a physicist named Thomas Parnell at the University of Queensland in Australia wanted to demonstrate something to his students. Pitch, the black tar-like substance used for waterproofing ships, looks and behaves like a solid. You can hit it with a hammer, and it shatters. Parnell wanted to show that it is in fact a liquid, just an extraordinarily slow one. So he heated a sample, poured it into a glass funnel, and let it settle for 3 years. In 1930, he cut the stem of the funnel open and left it. He waited 8 years. In December of 1938, the first drop fell. The second fell in 1947. Parnell died the following year, in 1948, having seen 2 drops fall in 21 years of watching. The experiment was then largely forgotten for a while, sitting in a cupboard, dripping. In the 1960s, a physicist named John Mainstone found it and became its custodian, and he looked after it for 52 years. In all that time, he never saw a drop fall. 3 fell on his watch. In 1979, he stepped out of the room for a few minutes and came back to find it had happened. In 1988, he was away over a weekend. In 2000, a camera had finally been set up to catch it, and the camera malfunctioned in the 20 minutes during which the drop fell. He said afterwards that he had been within a few meters of the thing hundreds of times and had simply never been looking at the right moment. John Mainstone died in 2013. The 9th drop fell in 2014, the year after, and it was recorded, and he never knew. I am not telling you that story because it is sad, though it is a little. I am telling you it because it is exactly the relationship a 1,000-year mission would have with everybody who built it. The experiment did precisely what it was designed to do. It worked perfectly. It just worked on a timescale that had no particular regard for the people who cared about it most, and it outlived both of them, and it is still going now, in a cabinet, in Brisbane, 99 years in, on its 10th drop. That is the honest version of what we are asking for. Not heroism and not tragedy. Just something that keeps going while the people who started it get old and stop, and somebody else picks it up, and then they stop too. There is one more category worth putting on the table, and it is the closest real-world analogue we have to the 4th bill, which is the long-running scientific measurement. Not a device that keeps working, but a program that keeps being funded and staffed and taken seriously year after year, producing a record that only becomes valuable because it is long. The best of them are on the order of a century. There is a collection of photographic glass plates at Harvard holding images of the sky going back to the 1880s, 500,000 of them, the only record of what the sky looked like before living memory. There are meteorological series in Britain that have been kept continuously since the 1800s. There is a measurement of the carbon dioxide concentration of the atmosphere taken on a mountain in Hawaii that has run without a break since 1958 and is the single most important dataset in climate science, and it is important precisely and only because nobody stopped. Here is the part that matters. Almost every one of those programs has come close to being cancelled at least once, usually for money. The Hawaii measurements nearly ended in their first decade. The plate collection sat neglected for years and came close to being discarded. Each of them survived because a small number of specific people fought for them in specific committee meetings on specific afternoons and won. A century of that, and it was touch and go. Now imagine 10 of those centuries in a row, with nothing coming back the whole time. And there is one more object I cannot resist mentioning, because it is the gentlest illustration of the whole problem. In a foyer at the University of Otago in New Zealand, there is a clock that has been running since 1864 and has never been wound. It is driven by the daily rise and fall of air pressure and temperature, which flexes a sealed box of air a little every day, and that tiny flexing is enough. It has stopped a handful of times, on occasions when the temperature simply did not change enough for a while, and each time it started again on its own when conditions returned. It asks nothing of anybody. It has outlasted every person who has ever looked at it. We have now walked through all 4 bills: power, matter, heat, and attention. And every one of them is a rate of loss rather than a wall. Watts per year, damage per year, joules per second, funding per decade. Nothing in this subject is a barrier you break through. Everything in it is a leak. Which leaves one question, and it is the one the title promised in its second half, and I have deliberately left it until now. Suppose all 4 bills get paid. Suppose the ship works and arrives. what is actually there? I think the answer is the strangest thing in this entire subject, and it is going to change what you think the last 2 hours were about. Every few years a comet arrives. It comes in from nowhere in particular, swings around the sun, grows a tail, and leaves again, and if it is one of the long-period kind, it will not be back for thousands of years. In 1950, a Dutch astronomer named Jan Oort sat down with the orbits of the ones that had been carefully measured, and he noticed 2 things about them. The first was that when he calculated how far out each comet swung at the far end of its orbit, the answers clustered. Not scattered evenly, clustered. A great many of them reached out to somewhere in the region of 20,000 times the distance from here to the sun, and then turned around. The second thing was that they arrive from every direction, not from the flat plane the planets orbit in. From above, from below, from anywhere. Put those 2 observations together, and there is only one thing they can mean. Out there, far beyond every planet, far beyond the region where anything has ever been mapped, there is a shell. A roughly spherical cloud of icy bodies surrounding the sun in all directions, so distant and so faint that not a single one of them has ever been directly observed in place. We only know it exists because occasionally one falls in. That cloud is called the Oort cloud, and now I need to tell you how big it is, because this is the number that reorders the whole night. The inner part begins somewhere around 2,000 times the Earth-Sun distance. The outer part is usually given as extending to about 100,000 times that distance. Some estimates put it further, at 150,000 or even 200,000. NASA's own material gives the range as 10,000 to 100,000 and states plainly that the outer boundary is not a sharp line, because there is no line. The density simply fades until it is indistinguishable from nothing. 100,000 times the Earth-Sun distance is 1.58 light-years. Read that again, and then remember what we have been doing all night. 1 light-year is inside the Oort cloud. You spend 1,000 years, you pay 4 impossible bills, you arrive at the smallest interstellar distance there is, and you are still in the sun's cloud. You have not crossed a boundary. You have not left. There is a second measure that says the same thing from a different direction. The sun's Hill sphere, the region where its gravity wins out over the pull of the rest of the galaxy, is roughly 1 to 2 light-years in radius. At 1 light-year, you are still gravitationally bound. If you shut the engines off over an unimaginably long time, you would fall back. The address you have spent your entire civilization's patience reaching belongs to this star. It is, in a very real sense, the outer end of the back garden. So what is in the back garden? Start with the answer everyone assumes, which is a star, and there is not one. The nearest star to the Sun is Proxima Centauri, and it sits 4.2465 light-years away. That is more than 4 times the distance we have been discussing. But it is worth asking the more general question, not where the nearest star happens to be, but how likely it is that any given light-year of space contains one at all. In this part of the galaxy, stars are spread out at a density of roughly 1/10 of a star per cubic parsec, which works out to about 4/1000ths of a star per cubic light-year. Now take a sphere with a radius of 1 light-year, which is the volume we are talking about tonight. Its volume is about 4.2 cubic light-years. Multiply that by the density, and you get the expected number of stars inside it. 0.017, 17,000ths of a star. Which means that if you dropped a sphere 1 light-year in radius anywhere in this neighborhood at random, there is roughly a 98% chance that it contains no star whatsoever. Not a dim one, not a faint one. None. That is not a fact about our particular corner being unlucky. That is what this part of the galaxy is like everywhere. Stars are so far apart, relative to their size, that the space between them is essentially all there is. If the sun were shrunk to the size of a grain of sand, the nearest other grain would be about 6 kilometers away, and between them would be 6 kilometers of absolutely nothing. So here is the position after 11 parts. The destination is not a destination. There is nothing at 1 light year to arrive at. There is no star, there is no world, there is no surface, there is nothing to orbit, and nothing to photograph, and nothing to land on. Whatever direction you choose, the overwhelming probability is that at the end of your 1,000-year crossing, you arrive at a point in space that is exactly like every other point in space, and you are still inside the cloud of the star you left. Which means, and this is worth saying clearly, that a 1 light-year mission does not exist as a real proposal. It never could. The first genuine interstellar mission has to be at least a 4 light-year mission, and every single bill we have priced tonight, the isotope, the alloy, the radiator, the institution, has to be multiplied by 4 before it becomes a real conversation. 4,000 years instead of 1,000. 40 half-lives of plutonium instead of 11. 4 times the institutional continuity, which is now longer than any human organization in the historical record by a factor of 3. Before we get to that, there are 2 things in that volume that we do know about, and both of them behave in a way that is worth understanding, because both of them are lessons in how misleading the word empty is. The first is the Oort cloud itself, which sounds crowded and is not. It is thought to hold trillions of icy bodies larger than a kilometer across, and if you gathered every one of them together, the total would come to only a few times the mass of the Earth. Trillions of objects, spread through a volume so enormous that the typical distance from one to its nearest neighbor is in the tens of millions of kilometers, comparable to the distance from here to Venus at its closest. If you were sitting on one of them, you would see nothing. Not a faint neighbor, not a distant swarm. You would see the sun as a bright star, and you would see the rest of the sky exactly as it looks from your garden tonight. A cloud in name only, and in statistics only. The second is the gas. The solar system is currently moving through a wisp of interstellar material about 30 light-years across, called the local interstellar cloud, and it contains roughly 3/10 of an atom per cubic centimeter. Not 300 atoms. 3/10 of one. And here is the part that ought to feel wrong. That gas is at about 7,000 degrees. Hotter than the surface of the sun. It would not burn you. It would not warm you at all. Temperature measures how fast individual particles are moving, and those particles are indeed moving extremely fast, but there are so few of them that the total energy they could deliver to your hand is essentially nothing. Heat is a crowd. What is out there is not a crowd. It is a few sprinters in an empty stadium. The very best vacuum ever created in a laboratory on Earth still contains something like 10,000 particles per cubic centimeter, which makes the space we are traveling through roughly 30,000 times emptier than the emptiest thing we have ever made. And yet, take a column of that gas 1 meter square and 1 light-year long, and you have collected about 5 milligrams of hydrogen, roughly the weight of a grain of rice. Cross it at 1/5 of the speed of light, and that grain of rice arrives as a beam of individual nuclei, each carrying millions of times more energy than anything in a hospital scanner, striking the front of your ship continuously for the entire journey. The emptiness is real. It is also, at speed, a sandblaster. Take that same gas and measure it by volume instead of by column, and the picture inverts again. A single cubic light-year of this apparently absent material contains around 70 times the mass of the Earth. The same substance, measured two different ways, is either nothing at all or 70 planets, and both answers are correct. That is the fundamental problem with intuition at this scale. The space is so large that a density beneath any possibility of noticing still adds up to a quantity beyond any possibility of imagining. I said at the start of this part that the second half of the question was the strangest thing in the subject, and so far all I have given you is an absence. No star, no destination, nothing there. That absence is not the strange part. The strange part is what fills it. Because that volume of apparently perfect emptiness, with no star in it and nothing to land on, is not empty at all. Somebody has worked out roughly how many solid objects are drifting through it at any moment, and the number is not small, and it is not a rounding error, and it is not zero. It is a number with 14 digits in it. On the 19th of October 2017, a telescope on the summit of Haleakala in Hawaii recorded a faint moving point of light. It was small, it was not especially bright, and for a couple of days it looked like an ordinary minor body of the kind that turns up every week. Then somebody fitted an orbit to it, and the orbit did not close. Every object that belongs to the solar system travels on a closed path. It goes out, it comes back, however long that takes. This one was on a path that opened outward at both ends. An object that had come in from outside would swing once around the sun and would leave forever, never to return, having never been here before. It was given the Hawaiian name Oumuamua, meaning something like a scout or a messenger from the distant past. It was the first confirmed visitor from another star system anybody had ever seen. In 2019, the second one arrived, discovered by an amateur astronomer in Crimea, and named Borisov after him. That one was unmistakably a comet, with a proper tail, made of material that looked chemically rather like our own comets, which was itself a small and pleasing discovery. Comets may form in much the same way around other stars as they do around this one. And on the 1st of July 2025, a survey telescope picked up the third. It is called 3I/Atlas, and its orbit is the most extreme ever recorded in this solar system. Its path is bent outward far more sharply than either of its predecessors. It came in at an inclination of 175 degrees, which means it was traveling almost exactly backwards relative to the direction the planets move. It passed closest to the Sun on the 29th of October 2025, at a distance a little further out than the Earth. And its speed relative to the Sun, far from it, before the Sun's gravity had done anything to it at all, was about 58 kilometers every second, more than 3 times faster than Voyager, achieved by nothing but the ordinary drift of the galaxy. Hubble looked at it on the 20th of August 2025 and could not pin its size down precisely, which is normal for an active comet wrapped in its own gas. The nucleus is somewhere between about 440 meters and 5.6 kilometers across. As it approached the Sun, it produced hydroxyl and cyanide, which are the ordinary signatures of a comet warming up, and also, more unusually, atomic nickel and iron. 3 of them in 8 years. And that is the number that lets you count everything else. Because these objects are essentially invisible. They are dark, they are small, and we can only see one when it happens to come close enough to the Sun to be lit up and to move fast enough across our sky to be noticed. To spot 3 in 8 years, from surveys that cover only a fraction of the sky and only catch the very closest passes, the actual population has to be enormous. The calculation has been done. Working backwards from what it took to detect Oumuamua, the estimated density of objects that size drifting through interstellar space is around 1/5 of an object per cubic astronomical unit. A cubic astronomical unit being a cube with sides as long as the distance from here to the Sun. Now carry that outward. 1 cubic light-year contains about 250 trillion of those cubes. Multiply, and you get roughly 50 trillion Oumuamua-sized bodies in every single cubic light-year of ordinary space. And a sphere 1 light-year in radius, the volume we have spent the whole night trying to reach, holds about 200 trillion of them. Set that next to the other number from the last part and hold them together, because this is the heart of tonight. Inside 1 light-year of the Sun, approximately 0 stars, and approximately 200 trillion loose bodies, each one at least the size of a large building, most of them considerably bigger, drifting through. None of which we can see, none of which are bound to anything. Every one of them thrown out of some other star system at some point in the last few billion years and passing through here on a path that will never bring it back. Let me put you there, because I want you to feel the shape of it rather than just hear the arithmetic. You are at the arrival point. 1 light-year out, in whatever direction you chose 1,000 years ago. Behind you, the Sun is still the brightest thing in the sky, not by a lot, but by enough that you could pick it out if you knew where to look. It gives no warmth. It is a star now, and nothing else. In every other direction, there is nothing. No planet. No surface. No landmark of any kind. You have arrived at a place defined entirely by its distance from somewhere else. And around you, silently, in the volume you are floating in, there are 200 trillion objects. Rocks and ice the size of city blocks and small mountains, spread so thin that the nearest one is likely to be further away than the Sun is from the Earth, moving on paths that came from stars you cannot identify and are going to stars that will not exist by the time they arrive. Not one of them is stopping. Not one of them is from here. They have been coming through this volume for as long as the galaxy has had stars in it, and they will keep coming through it, long after ours has gone out. You have traveled for 1,000 years to reach the emptiest place you can imagine, and it turns out to be a road. And you are the slowest thing on it. I should say something here about a conversation that has attached itself to these objects, because it comes up every time one is found, and it deserves a fair hearing rather than a dismissal. There is a real anomaly in the Oumuamua data. As it left, it accelerated slightly more than the Sun's gravity alone can account for. In a comet, this is completely routine. Gas venting off the sunward side gives a gentle push, and astronomers correct for it as a matter of course. But no tail was seen on Oumuamua at all, and no obvious venting. So there is a genuine, published, unresolved question about what pushed it. The leading natural explanations involve outgassing of substances that would be very hard to see, such as hydrogen or nitrogen ice, and neither is confirmed. From that unresolved push, some people have argued that the object was manufactured. And the honest response is not derision, it is a distinction. Unexplained and artificial are not the same category, and the history of this field is full of anomalies that were real, that took decades to settle, and that turned out to be ordinary in an interesting way. The Pioneer spacecraft were observed for 30 years to be decelerating slightly more than they should have been, and papers were written proposing new physics, and the eventual answer was that the spacecraft were radiating their own waste heat slightly more in one direction than another, and gently pushing themselves. Real anomaly. Real puzzle. Perfectly mundane cause. And it is worth noting that the 2 visitors we have seen since Oumuamua both behaved like comets and looked like comets. Borisov chemically ordinary, 3I/Atlas venting exactly the substances a warming comet should vent, on exactly the schedule it should vent them. 3 detections in 8 years is also, precisely, what the improvement in our survey telescopes predicts for a natural population. Nothing about the count requires anything unusual. That will change soon, incidentally, and in the best possible way. A new survey observatory in Chile has begun a 10-year program of photographing the entire visible sky every few nights, and it is expected to raise interstellar object detections from a curiosity to a catalogue, possibly dozens a year. At that point, the number I gave you a moment ago stops being an extrapolation from a single object and becomes a measurement. There is a fourth category, and it is still being counted. When a massive object passes directly in front of a distant star, its gravity briefly bends and focuses that star's light, making it appear to brighten and then fade over hours or days. Surveys watching millions of stars for exactly this effect have been finding brief brightenings that correspond to objects of planetary mass with no star anywhere near them. Free-floating planets. Worlds that were thrown out of the systems they formed in and now drift alone in the dark forever. Nobody knows how many there are, and the estimates are startling. One analysis of 9 years of survey data implied something like 20 free-floating or very distantly orbiting planets for every star in the galaxy, which would put the total in the trillions. A new telescope designed partly for this work, the Nancy Grace Roman Space Telescope, is expected to find around 400 Earth-mass rogue planets during its main mission alone. And in January of 2025, a team published the first measurement of both the mass and the distance of one of these objects simultaneously, which is the point at which they stop being a statistical inference and start being individual things with properties. Whether one of them is inside our 1 light-year sphere right now is not a question anybody can currently answer. But it has stopped being a fantasy and become a probability, and that is a real change. And then the last item on the census, which is the one that turns the whole picture around. Things come to you. About 70,000 years ago, while anatomically modern humans were alive and looking at the sky, a small red star, and its even smaller companion, passed within about 52,000 times the Earth-Sun distance of us. That is roughly 8/10 of a light-year, closer than the distance we have been discussing all night. It is called Schultz's star, and the calculations give a 98% probability that it passed straight through the outer Oort cloud. Somebody saw it. Nobody wrote it down. And there is one on the way. A star called Gliese 710, currently about 60 light-years off, is heading almost directly at us. In about 1.28 million years it will pass within roughly 17/100ths of a light-year of the Sun, 25 times closer than Proxima Centauri is now. The figure is a probability band rather than a point, but the band is tight. 99% confidence that it falls between about 15 and 19/100ths of a light-year. It will move slowly enough to stir the Oort cloud thoroughly as it goes by, and the likely consequence is a long shower of comets falling inward for a very long time afterwards. So the sphere is not a room. It is traffic. On the timescales we have been forced into tonight, thousands of years to cross it, millions for the galaxy's own motion. Everything in it is moving, including the stars, including us. Which brings us, finally, to the answer. Imagine a single sheet of paper on a desk, with a list written down the middle of it, and nothing else in the room. This is the manifest. This is what it really takes to travel 1 light-year, itemized, with nothing removed to make it sound better. Item 1. A power source that still delivers useful electricity after somewhere between 1 and 4,000 years. The best isotope currently flown loses half its output every 88 years and is down to 0.03% after a millennium. The best isotope anyone is developing lasts about 430 years per half, arrives 5 times heavier for the same warmth, and is down to 1 part in 10 million after 10,000. No known arrangement of matter delivers what this line requires. Nothing on the market. Nothing on the drawing board. Item 2. A body, structure, wiring, optics, memory, mechanisms that holds together for the same duration with nobody aboard and no repair. The environment hardens metal until it cracks, cuts the long molecules in every plastic until they craze, fills semiconductors with trapped charge until the circuits drift out of specification, evaporates every lubricant, and fuses moving parts into single objects. We have 50 years of data. Every claim beyond that is an extrapolation of 20-fold, and the experiment we are extrapolating from is down to 2 working instruments. Item 3. A radiator larger than any structure human beings have ever assembled anywhere. Because the only way to get rid of heat in space is to glow, and glowing at a temperature useful to anything delicate means about 460 watts from each square meter, which means tens of thousands of square meters of thin panel that must survive Item 2's environment for Item 1's duration. And Item 4. An organization back here that is still competent and still funded and still pointing a dish at the right patch of sky when the answer arrives, for longer than any human institution in the historical record, except a handful of universities, a parliament, and 1 Japanese temple-building family. Continuously. With nothing coming back the entire time to justify the expense. That is the bill. That is what it really takes. And notice something about the whole list, now that it is sitting on 1 page. Not 1 single line on it is about going fast. Not 1 line is about thrust, or fuel efficiency, or trajectory, or any of the things people picture when they think about this problem. The engine is the part we already understand. I said that to you 2 hours ago as a kind of reassurance, and I want to hand it back to you now with the meaning turned around. Every part of this journey that we can calculate precisely, elegantly, to as many decimal places as anybody wants, is the part that was never in doubt. And every part that actually decides whether the mission works is a thing we have never measured, have no data on, and cannot test inside a human lifetime. The precision is all in the wrong place. We have exact answers to the easy questions and no answers at all to the hard ones. And the reason it looks like a physics problem is that physics is the only part of it we can see clearly. Look again at what each of the 4 bills actually is. 4 watts a year. Damage per year. Joules per second. Funding per decade. Every one of them is a rate. Not one of them is a war. There is no barrier out there to break through, no limit to beat, no threshold to cross. There is only loss, running quietly and continuously in every direction at once, and the only way to win is to arrive before enough of it accumulates. Which means the enemy in this subject was never distance. It was always duration. Speed is not valuable because it covers ground. Speed is valuable because it buys you less time in which to fall apart. That is the first answer. Here is the second, and it is what you would find. Nothing. At 1 light-year, there is no star, with about 98% probability. There is no world. There is no surface, no orbit, no landing, no photograph worth taking. And you have not even left home. The sun's cloud of comets extends to 1.5 times that distance, and its gravity holds sway out to further still. You would arrive, after 1,000 years, at the far end of the back garden, gravitationally bound to the star you departed from, with the sun still the brightest thing in your sky. The place is not empty, though. That is the strange consolation in it. 200 trillion loose bodies are drifting through that volume, city blocks and small mountains of rock and ice, every one of them thrown out of somewhere else, none of them from here, none of them stopping. 30,000 times less gas than the emptiest vacuum we can make, and 70 Earths of it in every cubic light year. And stars that come to you, in their own time, on their own errands, one passed within 8/10 of a light year while our ancestors watched, and another is due inside 2/100 of that distance in just over 1,000,000 years. So the honest version of the second half is this. There is nothing at 1 light year to arrive at, and there is a great deal there to meet. It is not a destination. It is a road. It has always been busy, and everything on it is going somewhere else faster than you are. And that leaves the third thing, which is the actual answer, and which I have been holding back all night. Go back to that sheet of paper. 3 of the 4 items are objects. An isotope, an alloy, a panel. Expensive, difficult, currently impossible, but objects, and objects can in principle be bought. Somebody could get rich, or a government could get ambitious, or a century of materials science could go well, and those 3 lines could be paid. The 4th line cannot be bought, because it is not a thing. It is a promise. Somebody, 1,000 years from now, in an organization that does not exist yet, speaking a language nobody currently speaks, has to consider it worth their morning to point a dish at an empty patch of sky and wait for a signal from people they have never heard of, about a question they did not ask, on behalf of a decision made before their entire civilization began. And nobody has ever successfully arranged that. Not once. The longest we have managed to keep anything powered and running is a bell in a glass case in Oxford, 186 years old, and the reason it has lasted is that nobody has to do anything. And this is not a soft observation about human nature. It is the hardest constraint on the list, and it is the one that has actually been studied. Everything else on the manifest has at least a research program attached to it, laboratories working on isotopes, on radiation-tolerant materials, on lightweight radiators, all of them making slow, measurable progress. The 4th line has no laboratory. There is no field of study whose subject is how to make an organization care about something for 40 generations, and there is no experiment anyone can run, because running it takes 40 generations. We know exactly how bad we are at this, because we have checked. The only serious, funded study our species has ever produced on speaking across 10,000 years concluded that language fails, symbols invert, institutions end, and the best available option is to build something ugly enough that a stranger's instincts do the work. And the message those engineers wrote, when they had exhausted every other option, was this: this place is not a place of honor. Nothing valued is here. What a starship needs is the exact opposite of that sentence, sent in the opposite direction. Not go away, but stay. Not nothing valued is here, but something valued is coming. Not a warning meant to survive without anybody remembering why, but an appointment kept deliberately by someone who chose to. Which means the most expensive component in interstellar travel is not on the spacecraft at all. It never was. It is continuity of attention, and it is the one item on the manifest that cannot be engineered, cannot be launched, cannot be tested, and cannot be replaced by anything cleverer. So, what does it really take to travel 1 light year, and what would you find? It takes a power source that outlives every isotope we have, a body that outlives every alloy we have tested, a radiator larger than anything we have ever built, and a memory longer than any institution that has ever existed. And what you would find, at the end of it, is that you never went anywhere. You were in the garden the whole time, watching the traffic. We call it 1 light year away. But away was never the right word, because away implies you left something, and you did not. The light from your lamp is still going tonight, out past the moon and the sun and Voyager and the comets, and it will still be going in a year, and it is not going away from anything. It is just going. Steadily, at the only speed there is, into a place that is far busier and far closer than anyone ever told you. And whether anything of ours ever follows it out there does not really depend on engines at all. It depends on whether anyone will still be listening.